All right. Here we go. Chapter 5.
I'm so happy.
So,
I'm so happy.
what we are going to start to do, and you're going to start to see a little shift in the class a little bit, is we're going to start to, we have a few more sort of core pieces, but we're going to start to see problems that combine different aspects of the stuff we've already learned. So you know all that stoichiometry stuff with the grams to moles and the balance equations and the mole ratios? We do that in every unit from now on. Every unit has that in it. Okay, so if your plan had been, I will real quick learn as little as I possibly can about this to try and make it through the test, that's not going to be a good plan. You need to know this stuff. You need to understand the balanced equations and the mole ratios. Those are the keys. So the next couple of units, we're going to be looking at using those mole ratios in slightly different ways with different starting points and different end points. One of the big things that we're going to do is look at different applications of these things to different sort of mediums, different ways that chemical reactions can take place. We've spent quite a bit of time talking about aqueous chemical reactions that take place in an aqueous solution. This unit is all about gases. We want to look at what is a gas, how do we describe a gas, what happens when gases react, how can we calculate all this kind of stuff. And fundamentally, our first question is, how do we measure, how do we describe gas behavior? And so one of the ways that we are going to sort of think about this stuff is in terms of rocketry. And I know a lot of you, I certainly as a kid, you know those rockets where you put some water into the little plastic red part of the rocket, and you put it on the little pump, and you pump it, and then you release the catch, and the rocket squirts out water, and it shoots up high in the atmosphere. That's the kind of rocket we want to be able to build. Okay? And to do that, to do it and sell it to our 1950s industrial military contractor guy, we need to make sure that our rocket meets certain specifications, that it goes high enough, that it, and so that's all going to be dependent upon how much pressure we can get it to generate. So, step number one, in order to build a rocket, one of these, and understand a water-powered rocket like this, a water and compressed air-powered rocket, is we have to understand what do we talk about when we talk about compressed air. When we talk about gases, how do we measure them? What is pressure? And how do gases behave? We know that the more pressure I put in the rocket, the higher it will go. Okay? So we want to think about, fundamentally, what is pressure? And our basic answer is pressure is the force of the collisions of the gas particles. Gas particles are constantly moving around inside their containers. When they hit the walls, that impact is what we measure as a gas's pressure. How hard they hit, how often they hit, those things determine how much pressure we say a gas is exerting on a container. Mathematically, pressure is defined by force times area. Force divided by area. So the area over which a force is acting. So, we want to look at how we can first measure, and then change the pressure in a container. Okay? So we know we want to build up pressure in our rocket. That's what's going to shoot the water out and have our rocket go up nice and high. But to do that, in order to increase the pressure, we have to be able to measure it. Okay? So our first goal is to be able to measure pressures. We typically measure pressures using a device called a manometer. And it is called a manometer, not a manometer. Okay? It is a manometer. Manometers are generally the tools that chemists use to measure pressures. They're really good in sort of gas pressure measuring devices. There are other types of ways to do it, but the manometer is sort of the first and the simplest way to do this kind of thing. So manometers are based around the concept of having a U-tube, okay? And not Y-O-U, but the shape of a U. So U-tube is a glass tube shaped like a U, okay? We do watch it, but we don't watch kitties dancing or anything. So the U-tube of a manometer is generally filled with a liquid, almost always mercury, because mercury has a very low vapor pressure. That is, it doesn't produce a lot of gases, and it's heavy. It's very dense. Okay? Now, the reason why we do that is to measure the difference in pressure between two sources. You can have a container, in this case our gas, that's going to have some particular pressure. And then in this case we have one that's open to the outside or open to the atmosphere, the gas all around us. And so we're measuring the difference in pressure between the gas and the atmosphere. But this could also be another gas connected in another chamber. You could do that as well. Now, the pressure difference is determined or measured by the difference in height of this mercury. Okay? So, in this picture, which pressure is higher? The gas or the atmosphere? Now, what about this picture led us to think that the pressure was higher in the gas? Eden? It's forcing the mercury down. It's pushing the mercury out of the tube against the atmosphere. And in fact, we can use this height as a measure of the differences in pressure between the two sources. This height difference represents a mass, a weight. The weight of this mercury represents a force that would be pushing downwards. That additional force that we would have to add to the atmosphere to equal the pressure of the gas. So we can measure the difference in pressure between these two as a height of a mercury column. And in fact, one unit of pressure that we use a lot is called the millimeters of mercury, mmHg. And so that mmHg, those millimeters of mercury, those are the pressure. That represents the pressure difference between the atmosphere and the gas. Another way mathematically to write that is that the pressure of the atmosphere plus the height difference is equal to the pressure of the gas. So this is a mathematical way to represent this relationship, where we could measure the pressure of the atmosphere, we could measure the height difference, and then use that to find the pressure for the gas. Question? It turns out it doesn't, because pressure is a per area unit, force per area. The shape of the tube doesn't matter, because the pressure will be proportional to the area that the tube is on.
Isn't the pressure and height in different units?
Well, we are going to use pressure in terms of millimeters of mercury. So that could be our unit for pressure. Our atmospheric pressure could be 760 millimeters of mercury. That's a very common unit to use for pressures. What would this picture look like if the pressure of the atmosphere was higher? How would it change? We'd go the opposite direction, right? The mercury would be higher on the gas side. And then this height difference, we'd have to move it to the other side. It would be added to the pressure of the gas. If the pressure of the atmosphere was higher, then it would be pressure of gas plus delta H. Or we could change the sign here to a negative. That would accomplish the same thing. It varies with the weather, but for our purposes, we generally assume it to be a constant. And we'll talk about it in a few minutes.
So you could always calculate the pressure of the gas and the pressure of the atmosphere?
Yeah, or vice versa. We have three variables, we got to have two of them.
So if pressure of atmosphere is high, then pressure of atmosphere minus 25.
Right, that would work. All right, so we talked about these millimeters of mercury, right? Yeah. There are other ways to measure pressure, having to do with how much a curved tube straightens. And that's typically how those kind of pressure gauges work. Yeah, we can look at pressure gauges later on. So, millimeters of mercury, they're also frequently called torrs, after the guy who invented the earliest barometers and manometers, Evangelista Torricelli, Italian chemist. So, millimeters of mercury, also called torrs. 760 of them is how we define one standard atmosphere. So at sea level, the nominal atmosphere of the Earth in monitor times is 760 millimeters of mercury. We define that as 1 atmosphere of pressure. So atmospheres are another unit that we use to measure pressure, ATMs, atmospheres.
So what torr is
1 torr is 1 millimeter of mercury. Now, the scientific unit, the System International unit for pressure is the Pascal. And a Pascal is a force of 1 Newton over 1 square meter. It's a very small pressure. Okay? So it takes a lot of pascals to equal 1 atmosphere. In fact, it takes 101,000 pascals to equal 1 atmosphere. So we typically work with kilopascals. Okay, kilopascals. 1 square meter. So kilopascals are used a lot more in certain applications than chemistry. Chemistry typically work in atmospheres or millimeters of mercury. The IB test tends to use more kilopascals because they're very correct on their System International stuff. So IB students, kilopascals.
Does that have any relation to Pascal's triangle?
I have no idea.
What about Mr. Scary?
Pasquale? Pascal is the last name of a guy who worked on this stuff. So I don't know if it's the same Pascal as the mathematician. It could be. I don't know. All right. So we can do conversions, right? 1 atmosphere, 760 millimeters of mercury, 101.3 kilopascals. Those are all equivalent pressures, okay? Now, the rocket that we're building, okay, our engineering fellows will tell us that to launch the rocket in the way we want, we need to get a pressure of 3,990 millimeters of mercury.
So what about pascals? So those are even smaller than kilopascals?
Yeah, 1 pascal would be 1,000th. There are 1,000 pascals in 1 kilopascal. Right? Kilo is the prefix for 1,000. So there's 1,000 pascals in 1 kilopascal. Just like there's 1,000 grams in 1 kilogram. So to launch the rocket, we need a pressure of 3,990 millimeters of mercury. How many atmospheres is that? Figure it out. Grab your calculator. I'm asking you to convert 3,990 millimeters of mercury into atmospheres.
5.62.
So we know that 760 for every 1. If you want to think about the dimensional analysis problem, what are we going to start with? What's the first thing we write down?
1 ATM for every.
What do we got? We start with what we know, 3,990 millimeters of mercury, and then we want to go from 760 millimeters of mercury to 1 atmosphere. Right? Do we get that? 5.25 atmospheres. Okay, so just a little conversion problem. We need to do these things. This happens frequently where we have to do these kinds of things. So what we need to do is we need to go ahead and think about what does it mean when we say atmosphere? What is atmospheric pressure? How do we measure that? Okay? And we're going to talk about a device, another device invented by Torricelli, the barometer. Okay? So barometers are, guys, devices that we use to measure atmospheric pressure. And they're based off of a column of liquid, usually mercury, but you could do this with water too, in a sealed container. Okay? This is something that you are all familiar with because you have all sat in a bathtub playing with plastic cups. Okay? I know you have.
I would always want us to stay so.
So, let's say we had a glass cylinder, okay, sealed at one end, and we are going to go ahead and fill that with water. Right? So I'm not in the bathtub, but I still get to play with water.
Me too.
So nice and full. I'm going to put my hand on here, and I'm going to turn this upside down. And we say, hey, just like in the bathtub, the water doesn't come out. Why not? Is there gravity still pulling on the water?
Putting down on the surface area and it's pushing the water up in the tube.
What's holding the water in this tube is the atmospheric pressure pushing on the surface of the liquid. Okay, we've all done this. If I let air come in, then that air creates space, right? Now the atmospheric pressure is holding this up. The air in here, I let a big bubble of air in, is at slightly lower pressure. How much lower is the pressure in here than outside? Could we measure that some way? If we measured the height of this water column, we could use that as a difference, because the height of this water column is going to measure the difference in pressure inside versus outside, just like our manometer did. Okay? So, we can let the water back out. And do I need this tub? Do I need this tub? Can I get the water to stay in here some other way? What's holding it in? It's the air pressure, right? The air pressure pushing on it. All I really need is something to keep the water surface from becoming unbalanced. Okay? Like a piece of paper. A piece of waxed paper in this case.
That's so cool.
Okay? So we do have to be a little careful. We don't want it to leak. Okay? So what's holding the water in? The air pressure around us is on the surface of the paper here. Okay? And so as long as I don't let the water leak out, okay, but I can take it off and the water will drop out. So yeah, you guys, you should, it's homework tonight. Go, you have to take a bath and bring plastic cups and, play with them. So,
That's so cool.
under normal conditions at sea level, the air pressure will support a column of mercury 760 millimeters high. So we'll have a column of mercury 760 millimeters high. As the air pressure changes, if a storm is coming or things like that, the column of mercury will fluctuate in height. That's how we measure atmospheric pressure. Okay? Like in the weather reports, they'll say the barometric pressure is so and so many bars or millimeters of mercury. That's the millimeters of mercury come from how high, literally how high is a column of mercury. Doesn't matter how big it is because the pressure is an area effect. It varies with area. As long as you have that height. The height is what's important. So, well then the tube will be filled all the way to the very top. Now, just like my tube was filled all the way to the very top, see the thing is mercury is about 13 times more dense than water. So if you wanted to do the same trick and use water as the liquid inside, you would need a column 13 times taller. It works out to be over 30 feet tall. So the air pressure will support a column of water over 30 feet tall. So you could use a building, for instance, to build a barometer out of water if you just need a really tall column. Okay? So atmospheric pressure can be measured using a barometer. That's where the 760 millimeters of mercury, that's normal atmospheric pressure. We'll measure a column that high. Now we get to the heart of the matter. Okay? We have a rocket with a pressure chamber that we want to compress. We want to get high pressure air in there. How can we generate higher pressures? The common one, the one that you all have done before, if you've ever used one of those little red rockets, if you've ever pumped up a bicycle pump to pump up your tire, you can change the volume. I have a pump. I have gases bouncing around inside here. This is a sealed container at some pressure and volume. Okay? So the ratio between the pressure and the volume equals some constant. As long as I don't change the temperature or let any gases in or out, this ratio will always equal the same number for a given setup. Okay? Now, what happens if I take this plunger and I push the plunger down?
The volume goes down.
So that we decrease the volume, right? The particles are still bouncing around in here. But now they're bouncing around in a much smaller space. How does that affect how they hit the sides? Do they hit the sides more often? Yeah. Because there's smaller space, so it takes them less time to get from one side to the other. So if they're hitting more often, that means the pressure went up. I have the same relationship, this same container, same temperature, same number of particles. If the volume goes down, the pressure has to go up to compensate. Pressure and volume are inversely related. Okay? So that's our first relationship about gases, pressure and volume. So if I want to take a pump and I want to pressurize my rocket, which has I know that my pump has some pressure volume. I know the rocket is going to have some pressure and volume. And I'm going to connect them, again, sealed container, no temperature change. If my rocket, I want it to get to 10 liters, that means my volume here is going to be 10 liters. And what pressure did we say we needed? 5.25 atmospheres, right? Now, with a normal pump, in a situation like this, what pressure does my pump start at? Yeah, it starts at 1 atmosphere. It's the air all around us that the pump starts with inside it. Okay, when I pull it up, it's pulling air in from the outside. That's at 1 atmosphere. It's the volume of the pump. I'm imagining a single action pump. I need a pump of a certain volume that I can press it down to push the air into the container. Okay? So I'm going to have just one cylinder that I'm just going to push down once to simplify our work. The question is, what volume of air at 1 atmosphere do I need to fill a container of 10 liters to 5.25 atmospheres? How can I solve for V? I need to take the 1 atmospheres and I need to move it to the other side. Right? Atmospheres cancel atmospheres. I'm left with 52.5 liters. In order to have a single pump the air to get my rocket 10 liters to 5.25, I need to start with 52.5 liters of gas. Okay, yeah, we're simplifying. Obviously, you could break that up into 52.5 pumps of a 1 liter pump. That would work in basically the same way. But we're just making it simple. So if we do that, we get our rocket all ready to go, but we load the rocket, we get it all ready in the afternoon, but we launch in the morning. Very common sort of setup. We have an evening to run all our checks and make sure the payload is working correctly and all that kind of stuff. So here's the problem though. The temperature is very different in the morning than in the afternoon. And we know that temperature has effects. Have you ever taken a balloon and held it over a warm oven or like a heater grate or hit it with a... You didn't? No? Or put it in front of a fire? Not in the fire. But if you ever do one of these things or put it in the freezer, okay? If you do any of those things, the balloon changes size. Balloons are essentially constant or a good simulation of a constant pressure device. Okay? When we change the temperature, the particles change. So we remember we have our same container. This time we have a temperature factor. We're now going to change the temperature. I've got the particles moving around. Okay? And now I'm going to not change the volume. I'm going to keep my volume fixed because this is like our pressure chamber. But what I'm going to do is I'm going to, let's say, heat this container up. Okay? So I heat the container up. It's now a much higher temperature. What happens to the particles if I heat them up? They move around faster. They bounce around. They hit the sides of the container more often. They hit it harder. They increase the pressure. If temperature goes up, pressure goes up to compensate at fixed volume. You could also imagine a situation, our typical balloon situation, where if the temperature goes up for a fixed pressure, balloons are basically a good approximation of a fixed pressure, the volume will go up. So if I take a balloon and I hit it with a hairdryer, it will expand. Okay, and eventually pop if I keep doing it, yeah. Or if I take a balloon and put it in the freezer or douse it with liquid nitrogen, it will shrink. Okay? And we can mathematically model that change.
Would that work with helium too?
Any gas. Okay, any gas.
Just ideal gases?
Well, yeah, ideal gases, we'll talk about real gases at the end of the unit, but ideal gases are what we're going to work on. So, we can now talk about the initial set of conditions, pressure, volume, temperature, and the final set of conditions, pressure, volume, temperature, and know that they are equal as long as we have a sealed container. So we can go back to our rocket and say, okay, we have a different temperature. Well, a rocket our launch temperature is about 0 degrees Celsius. It is cold in the mornings where we launch our rocket. And we know that we pump it up in the afternoon the day beforehand, so it's at about 25 degrees Celsius. We want those two things to be equal somehow. Does anybody see a fundamental issue with this equation, the way I've written it? Yeah, I've got this divide by 0. It's not a good plan, right? If only we had some sort of temperature unit that would allow us to never have to worry about 0, which would be kelvins. Remember, kelvins are the unit, the scientific unit for temperature. And there's a really good reason for that. Because you can't have 0 degrees Kelvin. 0 degrees Kelvin, absolute 0, is what we define as the 0 point of energy. And you can't actually get to that 0 point. Okay? Well, so we need to convert 0 degrees Celsius into kelvins. How do we do it? Anybody know? I know. Okay. What's the ratio? What's the conversion? 273. We're going to take 0 and add 273 to convert that to kelvins. Question?
I was wondering, because before you said that with decrease of volume there's an increase of pressure.
Yeah.
But then with the temperature, volume, pressure, there's the increase of temperature, an increase of pressure, and increase of temperature, and increase
Yeah.
of volume.
It depends on what's being held constant. And so you can, all three of them are related. You can change temperature and change volume. You can change volume and change temperature. In fact, frequently, if you've ever actually done any pumping, like with a bicycle pump, it gets hot. When you compress the gas, actually the temperature does increase in addition to the pressure increasing.
So when you convert from Celsius to Kelvin, do you only always add
273.15, some other digits, it's a measured value.
But it's all just adding.
You add 273 Celsius to kelvins. You take the temperature in Celsius and add 273.15. If you have kelvins you want to go back, you subtract 273.15. Yeah, they use the compression to heat, yes, until you hit the ignition point. So 25 plus 273 is 298. Now we're at a point where we can do this calculation. What do I need to do to make this work?
Isolate the variable.
I gotta isolate the unknown. So what do I have to do to the 298? Yeah, I gotta times it to the other side. So we shift that over there. And the 1 atmosphere, that again, that comes down to the bottom over here. Okay? And so we have a volume, this time we need 57.3 liters. Okay? So with the lower temperature, we need a larger starting volume. Okay, we need a little bit higher pressure to start with because when we cool it down, the pressure drops. Question?
In our worksheet, it says, first of all, in Charles' law, it says B equals lowercase b times temperature.
So the lowercase b is just a constant.
And what about for Avogadro's law, B equals lowercase
We're not there yet.
A?
We're not there yet.
I thought that's what you just did.
Nope.
Okay.
This is Avogadro's law. All right. So Still having some troubles getting to the proper pressure at launch time. Okay? And so we have our engineers are going through and checking out the rocket, double checking the chamber and stuff. And what happens is our pressure is still too low, but they notice that there's a sort of white crystalline solid that's forming inside the chamber. What temperature are we at? 0 degrees Celsius, right? Now, when we pump the rocket up, when we add the air, and we are taking air, what is air made up of? What is the number one component of air? Nitrogen gas, 78%. Okay, then oxygen is next. And you've got carbon dioxide. And the thing that a lot of people forget, there's quite a bit of water vapor. There's quite a bit of water vapor in the air as well. Okay, and that fluctuates a lot with temperature and pressure. Okay, how much water vapor there is. Also, the environment. How much water do you have around you? Right? If you're next to the ocean, you're going to have a lot of water vapor in the air. So, this white stuff could very well be water that's condensed into ice. And so what we need to think about is, how do the number of molecules, how do the number of particles affect this? If I have my typical container, and the little particles are bouncing around, and I've got measuring the pressure, the volume, the temperature, and the moles now, when I cool this thing down, some of these particles fall out. They become a solid. I now have fewer particles. How is that going to affect the collisions? Fewer particles, fewer collisions. So when I look at this situation here, there are just fewer collisions taking place. And what that does is it changes this N value. N is the moles of gas. If this goes down, then the pressure will go down at the same time, assuming constant temperature and volume. Mass doesn't matter. The mass doesn't matter because the temperature is what's going to tell us essentially how fast the particles are going to be moving. We'll talk a little bit more about the relationship between temperature and mass in a couple of days. But it's really the number of particles that's important for the collisions, because the mass of any one particle is pretty insignificant compared to how many of them there are.
Does it matter if it's upside down or sideways?
No, the gas particles move around in straight lines, essentially independent of all that stuff. Well, you might get some striation, but gases mix really well because of the fact that they are not bound into a certain volume. They typically expand to fill the entire volume really well. Certainly to any kind of first approximation of any of the work we're going to do, we don't have to take into account any kind of real world effects. In fact, we call gases that behave like this ideal gases. And we'll talk a bit about the difference between ideal and real gases towards the end of this unit.
Is there a relationship between moles and temperature?
Yep, all these things are related. You can set any of them to be constants, and I can now start to look at problems where I have, some set of initial 4 conditions and some set of final conditions, and I can vary all of them. As long as there's only one unknown, you can solve the math.
So, increase in temperature is decrease in number of moles.
It could be if you set up the container right. The key here is that you have to have a container where the number of particles is somehow controlled by the temperature.
That's what the equation is representing right there.
This equation, what I've represented is that the number of particles go down, and that decreased the pressure. In this equation, I've kept the temperature and the volume constant.
Wait, where do the moles go if the temperature goes up?
It would depend on your container, but if you had a container with a leak, as the temperature increases, the particles tend to leak out faster
Oh, because they're moving faster?
because they're moving faster. And we'll learn about that. It's called diffusion. Well, it's called effusion, actually. We'll learn about it.
What is the moles? Is that the moles of it as a gas? Or
The moles of gas. The moles of gas.
solid?
Then the moles go down. And that's exactly what happened here. The moles went down. So we know our rocket, 5.25 atmospheres, 10 liters, 273, and we need 2.34 moles of gas particles. Now our pump, to accommodate the loss of water, has to have 2.54 moles. That's the water that's going to freeze out. Okay? 1 atmosphere, 298. Again, we want to solve for V. What do I got to do? I've got to isolate that variable. Take these guys, we're going to move them up to the top over there. We're going to take the 1 atmosphere, put it on the volume, and we can solve. Okay? This is what we call an initial and final states problem. I'm given a set of initial conditions, I'm given a different set of final, and I just plug them into the equation. If there are some variable that doesn't change, say the temperature is held constant, I drop temperature out. PV over NT equals PV over NT. And I can control all, I can change all of them, I can change just one of them, do whatever I want. Okay? Right. I gave you all those numbers but the one for volume. So it's going to look something like this. Here is a smaller test rocket that we're using. It has a pressure chamber that holds 2.5 liters. Needs to be pressurized to 2.25 atmospheres at 0 degrees Celsius. And we need it to contain 2.51 moles to get enough force, enough propellant to launch our rocket. What volume of the pump, what volume would our pump need to be if the pump starts at 27 degrees, 105 atmospheres, and contains 2.75 moles? How many variables in this equation? How many numbers have I given you? I gave you 7 numbers because there's 4 on each side, right? An initial pressure, an initial volume, initial temperature, initial number of moles. I changed all of them, and I've asked you to find one. All right? Take a sec. Do this problem. So your initial setup should have looked something like this. 1.05, 300 Kelvin, 0.275, the volume we don't know. This is our pump. 2.25 atmospheres, 2.5 liters, 273 Kelvin, 0.251 moles. This is our rocket. Okay? Initial and final states, initial and final conditions. We can rearrange this to solve for V. I'm going to move the 300 times 2.75, multiply each side by that. So 300 times 2.75 comes up on the top on the right-hand side here. And then I've got my 1.05 on the bottom. So this should have, I see 3 sig figs. If we assume that there's a decimal point here, which is reasonable. 6.45? All right, looks like we're ready to launch this rocket. So we've got all the variables nailed down. We can talk about pressure. We can talk about volume. We can talk about moles. We can talk about temperature. We can control all of the variables. We are ready to launch our rocket. I went back too far. Give me a sec. Okay? We got to move on. You can watch it. You can check it out tonight. So, we've got all the variables nailed down. Now we're ready to launch a water rocket. So, this is a water-powered rocket. High pressure air and water shooting out of that rocket. They get a couple hundred feet high. Okay? Trigonometry. You could also, yeah, you could do calculations based on, there's some physics calculations you could do. Yeah, you have to take into account air resistance. It's doable. I mean, yes.
Well, we have to know how to do that in test.
Not in this class. Physics. All right, so what we've been working with is actually called the ideal gas law. Any gas that follows this law is called ideal, and pretty much most gases under high temperature and relatively low pressure conditions. Okay? So room temperature, room pressure, those are all good conditions for most gases to behave ideally. That is that the relationship between pressure, volume, moles, and temperature is always equal to the same number, like always in the universe. We call this the universal gas constant, and it's equal to 0.0821 atmosphere liters per mole Kelvin. So any conditions for a gas, any container, any description of a gas, if you know the pressure, volume, moles, and temperature, it's going to equal this value. So you can solve this equation directly. If you know 3 of these variables, that work that we did with P1 V1 over N1 T1, we didn't need that other half of the equation. Because that other half of the equation we did, the one where we knew all 4 variables, was equal to 0.0821. Always. Okay? It's the way gases behave under ideal conditions, which is most of the time. So we can rearrange this equation to solve pressure times volume equals moles times RT, or PV equals nRT. Pervnert. All right? What is R? R is 0.0821 atmosphere liters per mole Kelvin. So I can give you problems now. Instead of giving you 7 variables, I only really need to give you 3. So I can give you set up an ideal gas law problem that gives you the volume and the number of moles and the temperature. Okay? So I gave you volume, moles, and temperature. And I'm basically asking you to find the pressure. And in this problem, I'm asking you to compare it to this maximum safe value. So I'm going to take these values, pressure, which I'm trying to find, times volume, equals moles times RT. R is 0.0821 atmosphere liters per mole Kelvin. If you change the units, the number value, the number part changes. Okay? These are the units for 0.0821. Yep, you'd have to convert. If they give you mmHg, convert it into atmospheres and use this number. Okay? So we, again, substitute and solve. We get a value of 8.43. That's above the safety rating. That's not a good idea.
Wait, what is the safety? What's the safety?
So this one, the pressure chamber was rated for 8 atmospheres of pressure. If you go above that, it's possible that it could fail. Now, typically, there's a margin of error built into those safety ratings, right? Those pressure ratings. But you wouldn't want to push it like that. You would not want to typically run a device at higher than its maximum rated pressure. You risk failure. And failure in high pressure conditions is very dangerous. That's called an explosion. All right? Yeah, you could get a higher rated pressure chamber. It costs more money. All right, so your turn. How many moles of gas do we need to fill our pressure chamber? 25 liters, 10.5 atmospheres, 15 degrees Celsius. How many variables, how many pieces of information did I give you? 3. Okay, I gave you 3 of the 4. I'm asking you to find the n value. And this all works because we know R is always the same number. R is not a variable. R is a constant, the universal gas constant. So your equation you're using equals nRT. So how are we doing? Got that set up? PV equals nRT. Pressure and volume we know. N we don't. R is always the same number. T, we took the 15 plus 273. PV equals nRT. We're going to take that. We need to rearrange to solve for N. 10.5 times 25 divided by 0.0821 times 288. And we get 11.1. Yeah, that's fine. It's the same math. So again, this is what we would call an ideal gas law problem. They gave us 3 of the 4 variables. We plugged it in. We solved for the one they didn't give us. What's interesting about these problems is they give us the ability to change pressure, volume, temperatures into pressure, volume, and temperature of a gas into moles. Why would moles be useful for us? So yeah, we could convert that into a mass, grams. But we could also do what kind of problems? Stoichiometry problems. If we had gases reacting, I have to know how many moles of gas are reacting. And then we could talk about how much products were formed, how much reactants are needed.
How would you weigh gas?
That's why we typically don't try to weigh gases, because it's difficult to do. We measure the pressure, volume, and temperature of the gas and calculate how many moles there are.
That's so good.
And then you can find the grams, the weight.
We could find the grams, but we don't need it. Right? In stoichiometry, what's the important thing? What are we always trying to convert grams into? Moles. Moles are what we need to work with chemical reactions, because chemical reactions happen based on the number of particles. Okay? So, this is great. We have a rocket. It works. We might want to do some modifications to it. Huh? Nope. That's an effect that we call buoyancy. Just like a giant ship that floats in the ocean doesn't have negative weight. It has a positive buoyancy. It displaces a mass of water greater than it weighs. And it's the water, the upward force of that water, that holds it up. Exact same thing with a helium balloon. It displaces more air. The mass of the air it displaces is greater than its own weight. And so the buoyant force, the air, holds it up. Yep, exactly what happens. Typically, though, as the pressure you go up, the pressure decreases, the volumes have to expand. So you can get additional lift that way. But at some point, you do reach an equilibrium point. Or the balloon pops. Yes.